Somewhere in the darkness between the stars, something is moving. It has no light. It gives off no heat. It leaves no trail across the sky. And yet it weighs as much as a dying sun, compressed into a point so dense that not even light can escape its pull. Astronomers call it a rogue black hole, a stellar corpse flung loose from its birthplace, drifting alone through the galaxy at tens of kilometers per second. And there could be as many as 100 million of them wandering the Milky Way right now. You have never seen one. Nobody has. They are the most silent, most invisible predators in the entire cosmos, and there is exactly one strange method that can catch them betraying their location. Tonight, we hunt the ghosts between the stars, and we ask what would really happen if one drifted too close to our sun. Before we go any further, if you find this kind of deep cosmic exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Picture something drifting through the empty space between the stars right now. Not a comet, not an asteroid, not a dead star that has cooled into the dark. Something far heavier than any of those. Something with the mass of 10 suns, or 15 suns, or maybe 20 suns, all squeezed into a region no wider than a small city. Its surface, if you could even call it that, is a boundary where the laws of physics as we know them stop making sense. Light itself cannot climb out. Radio waves cannot leak out. There is no glow, no heat, no signal of any kind, and crucially there is no companion star orbiting it, no swirling disk of hot gas around it, nothing at all to reveal that it is there. It is simply moving, silent and unseen, at some tens of kilometers per second, through a region of the galaxy where nobody happens to be looking. This is a rogue black hole, and the reason you have never heard anyone talk about them the same way we talk about the famous supermassive giants at the centers of galaxies is that these things are almost unimaginably harder to find. They are the loners of the cosmos, cut off from every mechanism that normally lets astronomers see a black hole in the first place. They are, in the truest sense, dark, and they're drifting through our galaxy right now in enormous numbers. Before we go further, we need to be careful with a word. When most people picture a black hole, they picture one of two things. Either they picture the monster at the center of the Milky Way, a supermassive black hole, roughly 4 million times the mass of our sun, weighing enough to anchor an entire galaxy in place. Or they picture the truly grotesque behemoths lurking at the hearts of distant galaxies. Black holes with millions or even tens of billions of solar masses, ripping stars apart and belching out beams of energy visible clear across the observable universe. Those are not what we are hunting tonight. Those enormous objects live at the center of the galactic gravity wells, deeply embedded, effectively motionless in the grand scheme. They are anchored. The rogue black holes we are chasing here are something else entirely. They are stellar mass black holes, modest by cosmic standards. Their masses run from roughly 3 suns up to perhaps 50 or 60 suns. And instead of sitting at the center of anything, they are wandering, untethered, through the outskirts and the disk of the galaxy, unbound to any partner. That word, unbound, is the key. In physics, being unbound simply means you are not held in a stable orbit by another body's gravity. You are free. You are moving at whatever speed and direction the events of your past gave you, and unless something dramatic happens, you will keep moving that way for billions of years. Most of the stellar mass black holes that astronomers have actually found over the last half century are not unbound. They are bound. They live in binary systems, orbiting a normal star, and that companion is the entire reason we ever spotted them. Here is why. When a black hole and a regular star orbit close to each other, the black hole's gravity strips gas off the outer layers of the star. That stolen gas does not fall straight in. It spirals around the black hole, forming what we call an accretion disk. As the gas spirals inward, it is compressed and heated to millions of degrees. At those temperatures, it does not just glow, it shrieks in X-rays, and those X-rays punch out through the galaxy and reach our satellites in orbit around Earth. That is how we first identified a stellar mass black hole, an object called Cygnus X1, in the early 1970s. It gave itself away because its unfortunate blue companion star kept feeding it, and the feeding was blinding in X-ray light. Every stellar mass black hole confirmed for the first several decades of black hole astronomy was found in essentially this way: through its companion, through the mess it made while eating. Take away the companion, and the whole detection strategy collapses. And that is exactly the situation of a rogue. It has no companion, it is not eating anything. In the deep vacuum between stars, the average density of gas is roughly 1 atom per cubic centimeter, which is thinner than the very best vacuum any laboratory on Earth has ever produced. A rogue black hole drifting through that emptiness is barely absorbing anything at all. There is nothing to compress, nothing to heat, nothing to make it shine. So even if you pointed the most powerful X-ray telescope humanity has ever built directly at one, at just the right distance, you would see absolutely nothing. Just empty sky. Which brings us to the strange and slightly disturbing question. If they do not shine, how many of them are actually out there? And the honest answer, worked out over decades of population modeling, is that the Milky Way is probably full of them. Estimates vary, but the most defensible numbers put the count somewhere between about 100 million and perhaps 200 million isolated stellar mass black holes drifting through our galaxy right now. 200 million dark, unblinking gravitational wells. To put that in perspective, the entire Milky Way contains something like 200 billion visible stars. So for every roughly 1,000 stars you can imagine on a starry night, there is statistically one silent black hole moving somewhere unseen among them, and that is a lower bound, not a ceiling. To understand where all these things come from, we need to walk carefully through the death of a truly massive star. Not any star, but a very specific kind, and only with a very specific ending. Our own sun, for comparison, will never make a black hole. It is nowhere close to the mass required. When the sun runs out of hydrogen fuel about 5 billion years from now, it will swell into a red giant, gently shed its outer layers, and settle down as a slowly cooling white dwarf about the size of Earth. That is a peaceful death. No black hole, no violence. The stars that make black holes are the outliers, the truly massive ones. To have any real chance of ending as a black hole, a star has to be born with a mass of at least about 20 times the mass of the sun, and probably more like 25 or 30 solar masses to reliably do it. Stars like that are rare. In a random population of stars in the galaxy, only about 1 in every 1,000 or so is born heavy enough to become a black hole candidate. But those rare heavy stars burn ferociously. Where our sun burns hydrogen calmly for about 10 billion years, a star of 25 solar masses burns through its supply in perhaps 5 million years. It is a brief, brilliant, catastrophic life. The reason such a star is doomed is a simple balance. Throughout its life, the star holds itself up against its own crushing gravity by nuclear fusion in its core. Hydrogen fuses to helium, releasing energy, and that energy pushes outward, exactly cancelling the pull inward. That balance holds the star in shape. But as the star ages, it burns through its hydrogen. It moves on to fusing helium into carbon, then carbon into oxygen, then oxygen into neon and magnesium and silicon, working its way through the periodic table, each new fuel burning faster and hotter than the last. Eventually the core is fusing silicon into iron, and this is where the star runs headlong into a wall built into the laws of nuclear physics itself. Iron is a dead end. Every element lighter than iron, when you fuse it, releases energy. Every element heavier than iron, when you fuse it, absorbs energy. Iron is the trough at the bottom of the curve. Once the core is iron, fusion stops paying its own bills. The outward push disappears. And in a fraction of a second, the core, which by now is roughly the size of Earth but holds more mass than the Sun, collapses under its own weight. It falls inward at something like a quarter of the speed of light. That is not a metaphor. That is real. In under a single second, an Earth-sized ball of iron implodes to a lump only tens of kilometers across. What happens next depends on exactly how heavy the star was to begin with. In the lighter cases, the collapse halts when the core has been crushed into a state so dense that its protons and electrons have been squeezed together into neutrons. The outer layers of the star, which were still falling, bounce off this hard neutron core and blast outward as a supernova. And what is left behind at the center is a neutron star, an object roughly the mass of the Sun, packed into a sphere the size of a small city. But if the star was heavy enough, even the neutron degeneracy pressure, the last known thing in physics that can hold a compact object up, is not strong enough. The collapse continues past the neutron star stage and vanishes into a black hole. Nothing that we know of can stop it. The event horizon closes over what used to be the core, and a new stellar mass black hole exists exactly where a burning giant used to shine. But here is the crucial detail, and the entire reason we are talking about rogue black holes at all. That final act, the supernova, is almost never symmetric. In principle, if you had a perfectly balanced star with perfectly balanced physics on all sides, the explosion would blow off the outer layers in a perfectly even sphere, and the newborn black hole at the center would remain exactly where the star had been. But nature is not that tidy. The convection currents inside the collapsing core, the way neutrinos escape, the messy hydrodynamics of the shock wave, the huge magnetic fields wrapped through the material, all of these are slightly lopsided, and when the explosion actually goes off, it goes off harder on one side than the other. That imbalance acts like a rocket engine. The newborn compact object, whether it is a neutron star or a black hole, gets kicked in the opposite direction. Astronomers call this the natal kick, and its size is not small. For neutron stars, which we can track by their radio pulses across the galaxy, the measured kicks routinely reach hundreds of kilometers per second. Some pulsars are moving faster than 1,000 kilometers per second relative to their surroundings, which is fast enough to blow completely out of the Milky Way over their lifetimes. Black holes seem to receive kicks that are somewhat smaller on average because black holes are more massive and it takes more push to move them. But the kick is still typically in the range of tens to a couple hundred kilometers per second. And that is enough. That is more than enough. A black hole, born inside a stellar cluster and kicked at 100 kilometers per second, will leave that cluster and drift out into the general galactic disk within a few million years. Once out there, in the thin fields between clusters, there is essentially nothing that can slow it down. It just keeps going. So the supernova kick is the first great machine the galaxy uses to make rogues. Every time a truly massive star dies, it may launch a brand new black hole outward like a bullet into the emptiness between the stars, where nothing catches it and nothing sees it. Over the roughly 13 billion years that the Milky Way has been forming stars, that machine has been running the entire time. Massive stars have been constantly born, burning brightly for a few million years, and dying in supernova explosions that fling their black hole cores in random directions. Even if the rate of massive star deaths in the galaxy is only about 1 or 2 per century, that is enough. Multiply 1 per century by roughly 10 billion years of active star formation, and you accumulate on the order of 100 million black holes made and released. The numbers really do stack up over deep time. But that is only the first mechanism. There is a second, and in its own way it is even more violent. It is called dynamical ejection, and it happens inside dense stellar clusters. In the crowded cores of globular clusters and young massive star clusters, stars are packed so tightly that they routinely pass close to one another. Once you have black holes in that environment, born from the deaths of the cluster's most massive members, the black holes tend to sink toward the center because gravity organizes things by mass. And at the center you get a black hole soup. Dozens or even hundreds of stellar mass black holes crowded into a region only a light year or two across. In that setting, 3 body encounters become common. A single black hole pairs up with another, and then a third one comes barreling in. 3 body gravitational encounters are chaotic in a very specific and well-studied way. In most 3 body encounters between compact objects, one of the 3 ends up ejected at high speed, while the other 2 are left in a tighter binary. It is essentially a gravitational slingshot. Energy is conserved. So the pair pulls closer together and the third object flies away, carrying the kinetic energy. In dense clusters, the ejected object can easily leave with velocities of hundreds of kilometers per second, sometimes even fast enough to escape the entire galaxy. Every one of those ejected black holes becomes a rogue. It heads out into the disk with no companion in sight, drifting under nothing but its own inertia. There is a third pathway worth naming, and it is subtle enough that it took decades of careful stellar evolution modeling to fully appreciate its importance. Most massive stars in the galaxy are not born alone. They are born in binary systems, or in triples, or in even more complicated hierarchical arrangements. Roughly 70% of all massive stars have at least one stellar companion at birth, and among the very heaviest stars, the fraction climbs even higher. That means that when one of those stars ends its life in a supernova, it is doing so with a partner nearby. What happens to that partner depends on the details, but a very common outcome is that the binary is disrupted. Here is why. Before the supernova, the 2 stars are held together by their mutual gravity, which depends on the total mass of the pair. When the supernova blows off the outer layers of the exploding star, a substantial fraction of that mass is suddenly gone from the system, leaving behind only the compact remnant. The gravitational tether that held the 2 stars together weakens instantly. On top of that, the natal kick to the newborn compact object throws it off its previous orbit in a direction that has nothing to do with the binary's plane. If the combination of mass loss and kick is severe enough, and it very often is, the binary falls apart. Both members go their separate ways. The newborn black hole flies off in one direction, carrying its natal kick, plus whatever orbital velocity it had before the supernova. The surviving companion star flies off in the opposite direction, carrying its own pre-explosion orbital velocity, no longer held by anything. Astronomers call these liberated companions runaway stars, and we have been finding them in the sky for over a century, moving through the galactic disk at speeds far higher than any of their neighbors, headed nowhere in particular. Every runaway star is the fingerprint of a supernova that happened somewhere else, long ago, that flung a partner loose. And for many of them, somewhere out there in the opposite direction, a rogue black hole was released in the same event, moving away with roughly equal and opposite momentum. So the binary disruption channel is really two mechanisms at once. Every time it fires, it produces both a runaway star that we can eventually see, and a rogue black hole that we cannot. And because such a large fraction of massive stars are born in binaries, this channel probably contributes as many rogues as either of the two mechanisms we discussed before, and possibly more. The runaway stars we do observe, catalogued for decades, are the visible tip of an invisible iceberg of released black holes drifting quietly through the disk. Between these two mechanisms, the supernova kick and the cluster slingshot, the Milky Way has been steadily filling up with untethered stellar mass black holes for as long as it has been making massive stars. Population synthesis models, which try to simulate the birth and death of stars galaxy-wide, converge on the estimate we mentioned earlier. Somewhere on the order of 100 million, and plausibly up to a few hundred million, isolated stellar mass black holes drifting through the Milky Way today. Not clustered, not in binaries, not feeding, not shining, just moving. Now, there is one more twist in how these objects are born that we should mention, because it complicates the picture in a way astronomers only recently came to appreciate. For the most massive stars, above roughly 40 solar masses in some models, the standard picture of a supernova explosion may not actually happen the way we expect. In these cases, the collapse is so violent and the core is so heavy that when the shock wave from the bounce tries to blow the outer layers off, it fails. It stalls. The outer layers of the star fall back onto the collapsing core rather than escaping. The star effectively swallows itself. Astronomers call this a failed supernova, or more colourfully, an unnova. From the outside, it looks like a bright, massive star that simply and quietly disappears one day. No fireworks, no dramatic explosion, just a slowly fading pinpoint until nothing at all is left but a black hole. We have actually caught what appears to be one of these events. Beginning in 2009, astronomers watching a giant star in the galaxy NGC 6946, some 22 million light-years away, saw it undergo a modest brightening and then quietly fade from view, never to return. There was no supernova, there was no fireworks, the star simply vanished. It is one of the strongest candidates for a direct collapse black hole ever observed. And these direct collapse black holes matter for our story because when a star collapses without exploding, there is no asymmetric supernova to kick the newborn black hole around. It just sits there. Or, if the star was already moving relative to the local rest frame of the galaxy, the black hole simply inherits that motion. It becomes an isolated black hole that is not violently rogue in the sense of being shot out of a cannon, but is nevertheless untethered, drifting, and just as dark as any other. There is also a subtlety in how massive stars actually end their lives that turns out to matter enormously for the black holes they leave behind, and that is the chemistry of the star itself. Astronomers use the word metallicity to refer to the fraction of a star's mass made of elements heavier than hydrogen and helium. In stellar language, everything from carbon up is a metal, including elements like oxygen and iron that we would not normally think of as metallic. The reason this matters is that heavier elements make a massive star's outer atmosphere far more opaque to the intense radiation streaming out from its core. When a very massive star is radiating enough energy to push against its own outer envelope, those heavier elements catch that radiation more effectively and use it to drive strong stellar winds. The star loses mass throughout its life, blown off into space by its own light. Now consider what this does. A high metallicity massive star, born in the modern chemistry of the Milky Way's disk, sheds a substantial fraction of its initial mass over the millions of years of its life. By the time it reaches core collapse, it may have lost half or more of the material it started with. Whatever black hole forms at the end is correspondingly less massive. A low metallicity massive star, by contrast, born in a chemically primitive environment, holds onto its material much more tenaciously. Its winds are weaker. When it finally dies, it collapses onto a substantially heavier remnant. This is why the black holes that LIGO and Virgo began detecting in 2015 through gravitational waves surprised so many astronomers. Many of them weighed 30, 40, even 70 solar masses, far heavier than anything anyone had inferred from X-ray binaries in our own galaxy. The most natural explanation is that those heavy black holes formed in low metallicity environments, perhaps in dwarf galaxies or in the early universe when the chemistry of star-forming gas was much simpler than it is today. The same physics shapes the rogue population. Rogues formed in the ancient generations of stars, when the Milky Way was chemically young, would tend to be heavier. Rogues formed in the modern disk, from stars enriched with the chemistry of many previous stellar generations, would tend to be lighter. The population we can potentially detect through microlensing today is a mixture across cosmic time, drawn from stars that lived and died at very different points in the galaxy's chemical evolution. When Roman does eventually measure the mass distribution of rogues, it will not be looking at a clean single value. It will be looking at a spectrum shaped by billions of years of the galaxy's chemical history. And there is one more piece of stellar physics that leaves a strange fingerprint on the rogue population, which is the pair instability mass gap. Somewhere in the initial mass range of roughly 130 to 250 solar masses, a massive star's core reaches temperatures so extreme that its photons begin spontaneously producing electron-positron pairs. Each pair production event steals a photon's worth of pressure from the core. Suddenly the core cannot hold itself up. It contracts violently. That contraction accelerates thermonuclear burning to explosive rates, and the entire star obliterates itself in a runaway thermonuclear detonation that leaves no remnant at all. No black hole, no neutron star, nothing. Just an expanding shell of enriched gas. The consequence is a gap in the mass function of black holes. Stars below the pair instability threshold, up to roughly 50 solar masses of final black hole mass, can form black holes normally. Stars in the pair instability window are destroyed entirely and produce no remnant. Stars above the pair instability window, above roughly 250 solar masses on the initial mass side, can collapse straight through the instability and produce black holes on the order of 100 solar masses or more. So the population of stellar mass black holes should show a gap somewhere between roughly 50 solar masses and 100 solar masses, a range in which no rogues should exist. Whether that gap is real is one of the questions Roman will help answer. If we find rogues in that mass range, we will know that some other channel must be filling in the gap. Perhaps hierarchical mergers of smaller black holes in cluster cores, or accretion from surrounding gas in specific environments. If we find that the gap is empty, or nearly so, we will have confirmed a striking prediction of stellar physics using an observational method that no one imagined would be possible a few decades ago. So, the population of galactic rogues is mixture. Some were born in violent kicks and flung across the disk at high speed. Some were born quietly and failed supernovae, and simply drifted where their parent stars had been going. And some were flung out of tight clusters by 3-body slingshots long after their birth. The velocity distribution reflects that mixture. Studies have measured proper motions in known black hole binaries, combined with theoretical models, suggest that isolated stellar mass black holes typically move through the galactic disk at somewhere between about 30 and 150 kilometers per second relative to the local stars, with a long tail of faster movers. That is a wide range, but the middle of that range is significant. Over 1 million years, a rogue moving at 70 kilometers per second sweeps across roughly 230 light years of galactic real estate. Over 100 million years, it can traverse tens of thousands of light years. And over 1 billion years, it can cross more than the full width of the Milky Way from edge to edge. That last point is worth sitting with for a moment. When you locate a rogue black hole in the sky, you are not looking at a fresh event. You are looking at the accumulated silent product of billions of years of galactic history. The one you might identify near the constellation of Sagittarius today may have been born in a stellar cluster that has since completely dissolved on the far side of the galactic disk more than 1 billion years ago. Its origin story is essentially unrecoverable. All you know is that a star died somewhere, sometime, and left behind a small dark object that has been moving in a straight line ever since. And this is where the sheer statistical weight of the population becomes eerie. If there really are 100 million or more of these things scattered through a galactic disk that is roughly 100,000 light years across and only about 1,000 light years thick, the average distance between any two neighboring rogues works out to something in the neighborhood of a few tens of light years. That is not close, but it is not astronomically far either. It is comparable to the distances between ordinary stars in our own neighborhood. Statistically then, there is very probably a rogue black hole within roughly 20 or 30 light years of the sun right now. Not one that is dangerous, not one that is heading anywhere in particular, just one that is there, drifting, unseen, and until only very recently, effectively unfindable. And that unfindability is the reason we can spend this entire discussion establishing that these objects exist without ever having pointed to a single confirmed example until the last few years. Everything about them conspires to hide them. They emit no light. They have no bright partner. Their event horizons are only a few tens of kilometers across, which at any interstellar distance is smaller than any telescope could ever hope to resolve. They move slowly compared to the vast emptiness they cross. So from our perspective, they barely shift position year to year. Every direct method astronomy relies on, brightness, motion, spectrum, temperature, structure, all of these methods depend on the object interacting with the electromagnetic universe, and a rogue black hole in interstellar vacuum simply does not, in any meaningful way. And so the census of the galaxy's dead massive stars remained a theoretical population, a number in a paper, an inferred crowd of ghosts, right up until a single stubborn piece of physics that Albert Einstein had sketched out a century ago finally caught one of them in the act. Everything about a rogue black hole is designed, almost cruelly, to hide it. And the frustration for astronomers is that we know they are out there. The math is not subtle. The population estimates from stellar evolution and cluster dynamics are robust enough that if the galaxy did not contain something in the neighborhood of 100 million isolated stellar mass black holes, our entire understanding of how massive stars die would be wrong. But knowing that a haystack contains millions of needles is not the same as picking one out. And for most of the history of astronomy, no working technique existed to pick one out. The rogues were, in every practical sense, invisible. To really feel that invisibility, it helps to walk through what a black hole in isolation actually presents to a distant observer. Start with the size. A black hole with a mass of 10 suns has an event horizon roughly 60 kilometers across. That is smaller than most cities on Earth. Now put that 60-kilometer object at a distance of even 100 light years, which is very close by galactic standards, and the angular size you would need to resolve is something on the order of a few billionths of a millionth of a degree. There is no telescope that's ever been built, and no telescope currently planned that can resolve a target that small at that distance. To directly image the surface of a rogue black hole, you would need an instrument with an effective aperture wider than the orbit of Pluto, and even then only for the very closest examples. Direct imaging is not on the table. It never will be. So we cannot see the object itself. Fine. In astronomy, that is normal. Most of what we know about the universe comes from indirect signals, not direct pictures. But those indirect signals all require the target to be doing something. To radiate, to move a companion, to disturb some gas, to leave a chemical fingerprint on light that passes it. And a rogue in the deep interstellar vacuum is not doing any of those things. Consider the vacuum itself. The regions between stars in the galactic disk contain, on average, roughly 1 hydrogen atom per cubic centimeter. In the thinner regions above and below the disk, that number drops to 1/10 of that, or less. A rogue black hole plowing through such an environment does technically capture some of that gas as it moves. This is called Bondi accretion, and its mathematics were worked out in the 1950s. The idea is simple. A black hole moving through a thin gas has a certain gravitational reach. Gas within that reach falls in. The problem is the arithmetic. A 10 solar mass black hole moving at 70 kilometers per second through a medium of 1 atom per cubic centimeter accretes something on the order of 10 to the 10th power grams per second. That sounds like a lot. It is not. It works out to less than 1/100th of a millionth of a millionth of the sun's own mass loss rate to the solar wind. And whatever tiny amount of gas does fall in, does not produce anything like the fireworks of an accretion disk in a close binary. The gas does not have enough angular momentum to spiral. It just falls straight down the gravitational well. Most of the energy released goes right through the event horizon along with the gas itself, never emerging as radiation. The efficiency of an isolated black hole at converting matter to light is essentially zero. Sound waves wouldn't help either, even if space carried them, which it does not. Neither would radio. The old dream of finding rogues through their radio emission runs into the same problem as X-rays. To glow in the radio, the black hole needs a magnetic field being wound up by infalling plasma, and there is no meaningful plasma to wind. Gravitational waves are similarly useless for isolated objects, because you need at least two massive bodies orbiting each other to make gravitational waves, and a single drifting black hole makes none. You might think, well, at least the black hole should absorb the light of stars behind it. If nothing else, it should cast a shadow. And in principle, that is true. But the shadow is on the order of 60 kilometers across, cast against a background of stars that are trillions of kilometers apart, seen from a distance of light years. The odds of a rogue black hole happening to sit precisely in front of a background star at the exact moment you are looking, in such a way that any measurable amount of light is blocked, are so small that this method never was seriously considered. For decades then, the situation was this. Astronomers were convinced that the galaxy was full of these things. Nobody could find one. And nothing in the standard toolkit of astronomy, none of the methods that had discovered every other kind of black hole, was going to work. Something new was needed. And that new thing had, in fact, been sitting on a shelf since 1916, waiting for the observational technology to catch up. Here is the single loophole. Even if a black hole does not emit any light of its own, and does not interact meaningfully with any nearby matter, and does not have a companion to betray it, it still has one property that it cannot hide. It has gravity. And gravity, we now know, does something remarkable to the light of any object that happens to pass near it. It bends it. Albert Einstein published the general theory of relativity in 1915. Among its many revolutionary claims was that mass warps the geometry of space-time around it, and that light traveling through that warp geometry follows the curves of the warp rather than moving in straight lines. In practical terms, a massive object like a star will deflect a beam of light, passing close to it by a small but calculable angle. The heavier the object, and the closer the light passes, the larger the deflection. Einstein calculated the specific angle a light ray would be bent as it grazed the sun. He predicted a deflection of 1.74 seconds of arc, which is a tiny angle, roughly the width of a coin viewed from a couple of kilometers away, but big enough to measure. That prediction was famously confirmed in 1919 by an expedition led by the British astronomer Arthur Eddington, who travelled to the island of Principe off the coast of West Africa to observe a total solar eclipse. During the brief minutes when the moon blotted out the sun's disk, Eddington photographed the stars whose light was skimming past the sun's edge on its way to Earth. Comparing their positions against reference photographs taken months earlier, when those same stars were in a different part of the sky and their light was not passing near the sun, Eddington confirmed that the stars had appeared to shift outward by roughly the amount Einstein had predicted. That result made Einstein internationally famous overnight. It also, quietly, established the physical principle that would eventually let us find rogue black holes 100 years later. Einstein himself thought about the further implications of light bending, and in 1936 he published a short paper on what would happen if one star passed almost exactly in front of another, as seen from Earth. He worked out that the foreground star's gravity would bend the light of the background star into a ring, now called an Einstein ring, and would also amplify its total brightness for as long as the alignment held. He concluded, somewhat dismissively, that there was no great hope of ever observing this effect for real stars, because the alignments required were vanishingly rare and the resulting rings would be far too small for the telescopes of his day. He was correct about his own era. He was, as it turned out, quite wrong about ours. The general effect Einstein described is called gravitational lensing. When the foreground object is a whole cluster of galaxies bending the light of galaxies behind it, we call it strong lensing, and it produces the spectacular arcs and multiple images that adorn Hubble Space Telescope images. But when the foreground object is much smaller, a single star or a stellar remnant, and it passes almost but not quite exactly in front of a background star, the geometry is different. The multiple images that form are far too close together for any telescope to separate. From our perspective, they blend into a single point of light. But the total brightness of that point does something measurable. It climbs, it swells, it reaches a peak, and then, as the foreground object continues its motion across the sky and the alignment breaks, it fades back down to normal. This is microlensing. And it is the tool that finally cracks the rogue black hole problem. The mechanics are worth understanding because they are what make the technique diagnostic. Imagine a background star sitting quietly somewhere in the galaxy, minding its own business. Now imagine an invisible massive object, our hypothetical rogue black hole, drifting through the foreground on a trajectory that will carry it almost directly across our line of sight to that star. As the black hole approaches the alignment, its gravity begins to bend the star's light noticeably in our direction, and the star begins to appear brighter than usual. As the alignment tightens, the brightening accelerates, sometimes reaching a peak amplification of a factor of 2, 5, 10, or in rare geometries, far more. Then, as the black hole slides past and the alignment breaks, the brightness fades back to baseline. From start to finish, the whole event is symmetric in shape, a single smooth rise and fall, characteristic and unmistakable once you know what to look for. The duration of the event tells you something specific. It depends on the mass of the lensing object, and on its speed and distance. For a stellar mass rogue black hole crossing our line of sight to a bulge star, typical event durations run anywhere from about 100 days to more than a year. That is roughly 10 times longer than the events produced by ordinary stars acting as lenses. Because a stellar mass black hole is significantly heavier than a typical foreground star. So already, from the duration of the brightening alone, astronomers can tell that they are probably not looking at a normal star acting as the lens. Something heavy is doing the bending. The reason duration works as a mass indicator, at least approximately, is worth spelling out. Any lensing geometry has a natural angular scale associated with it, called the Einstein radius, which sets the size of the ring the background star would form if the alignment were exactly perfect. That radius depends on the mass of the lens, on the distance from us to the lens, and on the distance from the lens to the background source. The heavier the lens, the larger the Einstein radius. The closer the lens sits to the midpoint between us and the source, the larger the Einstein radius. The physical scale is not enormous. For a stellar mass rogue at half the distance to the galactic bulge, the Einstein radius on the plane of the lens works out to something on the order of an astronomical unit, a few 100 million kilometers, which is roughly the distance from the Sun to Earth, Not a coincidence. The physics of gravitational bending sets that natural scale for any stellar mass lens at galactic distances. Now, think about what that means dynamically. A microlensing event begins when the lens moves close enough to the line of sight that the alignment enters the region set by the Einstein radius, and it ends when the lens moves out of that region. The event's duration is simply the time it takes the lens to cross its own Einstein radius against the background of the source, which is set by the lens velocity across the line of sight. Divide radius by velocity, and you get duration. This is why heavy lenses produce long events, and why measuring the duration alone does not give you the mass. A heavy lens moving fast can produce the same duration as a light lens moving slow, or a nearby lens can mimic a distant heavier lens. Duration on its own is a combined quantity that folds mass, distance, and velocity together into a single ambiguous number. To separate them, you need a second, independent measurement. That geometric fact is the foundation on which every rogue black hole detection ultimately rests. But duration alone is not enough. Something heavy could also be an ordinary massive star, or a heavy binary, or a stellar cluster projected onto the line of sight. To specifically say, we have caught a black hole, and to actually measure its mass, we need a second signature. And here is the beautiful part. Microlensing, done carefully enough, provides that second signature for free. Because in addition to brightening the background star, the foreground lens also physically shifts its apparent position on the sky. Just a little. Just a few tenths of a millisecond in the case of a stellar mass lens acting on a background star in the galactic bulge. That is far too small a shift to see with your eyes at any telescope. It is smaller than the diffraction limit of most ground-based instruments, blurred out by the atmosphere. But it is exactly the kind of measurement the Hubble Space Telescope, sitting above the atmosphere with its diffraction-limited optics, can just barely make. And that astrometric shift, that tiny wobble in the position of the background star during and after the microlensing event, is what breaks the degeneracy. It tells you specifically how far away the lens is and how heavy it is, as separate numbers, rather than combined into a single ambiguous parameter. There is one further technique worth naming, because it played a supporting role in the years leading up to the first confirmed detection and continues to be used today. It is called satellite parallax, and the idea is elegant. If you observe a microlensing event from Earth, you see one particular light curve, the rise and fall in brightness of the background source. If you simultaneously observe the same event from a spacecraft sitting somewhere else in the solar system, say in orbit around the Sun at a distance different from Earth's, you see a slightly different light curve. Not much different, but the peak brightness happens at a slightly different time, and the shape of the rise and fall is slightly offset. This is because the two vantage points are seeing the alignment through slightly different geometries. The lens sits at a fixed distance and the two observers are separated by a known baseline. So the lensing signal shifts by an amount that depends directly on how far away the lens actually is. Combine the ground-based light curve with the space-based light curve, do the trigonometry, and you get a purely geometric distance to the lens. Astronomers have used the Spitzer Space Telescope, and more recently the Kepler mission during its extended K2 phase, for exactly this purpose. When a promising long-duration event was identified from the ground, teams would rush to schedule follow-up observations from Spitzer while the event was still active. The results were remarkable. For dozens of microlensing events over the past decade, satellite parallax pinned down the distance to the lensing object to much better precision than would have been possible from Earth alone. That distance measurement, combined with the ground-based light curve, gave a clean mass estimate. Several isolated stellar mass compact objects have been identified this way, though the population of confirmed black holes remains small because most of the events turn out to be less exotic objects like faint stars or brown dwarfs. The technique is a beautiful illustration of what modern observational astronomy has become. You catch a rogue black hole by watching a distant star brighten. You confirm it by measuring, from two different points in space, the tiny difference in how that brightening looks. You then wait a decade for the Hubble Space Telescope to measure the astrometric wobble left in the background source. And at the end of all that, you have a mass, a distance, and a velocity for an object that has never emitted a single photon of its own. So the recipe emerged, in principle, decades ago. Monitor tens of millions of background stars, especially in the direction of the galactic bulge where the density of both foreground lenses and background sources is highest. Wait for one of those stars to undergo a long-duration microlensing event with no visible foreground star at the position of the lens. Then follow up that event with precise astrometry over several years, using a telescope like Hubble to measure the tiny position shift of the background star, deduce the mass of the invisible lens, and confirm whether or not it is heavy enough to be a black hole. The story of how microlensing became a working astronomical technique in the first place is worth telling briefly, because it did not begin as a search for rogue black holes. It began as a search for something else entirely, and the discovery of rogue black holes was almost an accident of the infrastructure that Hunt built. In the late 1980s, astronomers had strong evidence that the outer regions of galaxies contain enormous amounts of dark matter, mass whose gravity we can measure, but whose light we cannot see. Nobody knew what the dark matter was made of. One of the leading candidates at the time was a class of objects called MACHOs, which stood for Massive Astrophysical Compact Halo Objects. The idea was that the dark matter might simply be a very large population of ordinary but faint compact objects. Brown dwarfs, old white dwarfs, isolated neutron stars, isolated black holes, sitting in the halo of the Milky Way in numbers large enough to explain the gravitational anomaly. If that was true, microlensing was the way to prove it. 3 collaborations set out to test the idea in the early 1990s. The MACHO collaboration, run by American, Australian, and British astronomers, used a dedicated telescope at Mount Stromlo in Australia to monitor millions of stars in the Large Magellanic Cloud, a satellite galaxy sitting well outside the plane of our own, whose stars would be lensed by anything drifting through the halo of the Milky Way between us and them. The EROS collaboration, standing for Expérience pour la recherche d'objets sombres, ran a similar survey from Chile using a French-led team, and the first generation of OGLE, then a modest ground-based survey led out of Warsaw, joined the effort by monitoring stars toward the galactic bulge to catch lensing events in the disk rather than the halo. Over the following decade, all 3 surveys detected microlensing events, many of them. The events were real, the technique worked. But when the results were tallied up, the number of halo direction events was too small, by a factor of several, to be consistent with dark matter being made mostly of compact objects in the mass range the surveys were sensitive to. MACHOs, whatever they were, could not be the dark matter. That negative result was one of the most important non-detections of the 1990s. It effectively ruled out an entire class of dark matter candidates and pushed the field decisively toward the search for exotic particles, which is where the dark matter question sits today. But the surveys had also demonstrated something else, almost as a side effect. They had proven that microlensing was a real, repeatable, sensitive tool for detecting the gravitational influence of otherwise invisible objects. And when astronomers went back to their catalogues and asked how many of the events that had been detected might be caused by isolated stellar mass black holes drifting through the disk, the answer was intriguing. Not zero, not obvious, but real candidates existed, buried in the data. The chase for rogues was born from the ashes of the failed dark matter search, using the same techniques and often the same telescopes. Turning that recipe into an actual detection took decades of quiet, ground-based work. 2 survey collaborations did most of the heavy lifting. The optical gravitational lensing experiment, universally known by its acronym OGLE, is a Polish-led survey run out of Warsaw University Observatory that has been monitoring the galactic bulge from the Las Campanas Observatory in Chile since the early 1990s. Its current generation instrument photographs hundreds of millions of stars every clear night, looking for any of them to brighten or dim. Alongside it runs the Microlensing observations in astrophysics collaboration MOA, which uses a telescope in New Zealand to do the same job from a different longitude, so that the bulge can be watched around the clock. Between them, these 2 surveys catch several thousand microlensing events every year. The vast majority of those events are ordinary. A regular star drifts in front of a background star, brightens it for a few weeks, and drift away. Astronomers catalogue these and move on. But a small fraction of the events last much longer, hundreds of days, and show no foreground star at the lensing position when astronomers go back to look with better instruments. Those are the candidate dark lenses, the events where whatever bent the light of the background star did not itself emit any measurable light. Since the mid-1990s, astronomers had been assembling a list of such candidates. But candidates were all they were. Without astrometric follow-up, there was no way to prove that any specific candidate was a black hole rather than an unusually faint low-mass star, or a neutron star, or some other exotic possibility. The event that finally broke the case was flagged in June of 2011. Both the OGLE and MOA surveys picked up a background star in the direction of the galactic bulge, roughly toward the constellation of Sagittarius, starting to brighten. Within a few weeks, it was clear that this was an unusually long event, and by the time it peaked and began to decline, it had lasted for nearly 270 days from start to end. That was extreme. That was in the top fraction of a percent of any event either survey had ever seen. The event was catalogued under the label OGLE-2011-BLG-0462, and it went onto the shortlist of the most interesting dark lens candidates ever seen. What made the case worth pursuing further was that even in the best ground-based imaging taken later, there was no visible foreground star at the position of the lens. Whatever had bent the light of the background source was simply not there in any picture. It had to be dark, and a dark object heavy enough to produce a 270-day microlensing event had to be a compact stellar remnant. It was either a very heavy neutron star or a black hole, deciding which required Hubble. Beginning in 2011 and continuing across the next several years, teams led independently by Kailash Sahu at the Space Telescope Science Institute and by Casey Lamb at the University of California at Berkeley pointed the Hubble Space Telescope at the location of the event to measure exactly where the background source was and how its position drifted with time as the invisible lens moved on. The astrometric shift they were looking for was on the order of 1 millionth second over the course of years. To put that number in perspective, 1 millionth second is the angle subtended by a small coin lying on the surface of the moon as seen from Earth. Measuring that shift on a single faint star in a crowded bulge field required essentially every trick the Hubble team knew. It required going back with Hubble year after year for over a decade, matching the star's position against a grid of reference stars, correcting for parallax, correcting for Hubble's own motion, and disentangling the tiny signal from every source of noise. By early 2022, both teams had enough data to announce results, and they did so essentially simultaneously in 2 papers, submitted within days of each other. And here the story gets scientifically interesting, because the 2 teams initially disagreed about what they had found. The Sahu team analysed their data and concluded that the lens was a black hole of roughly 7 solar masses, sitting about 5,000 light years from Earth, moving at about 45 kilometers per second. The Lamb team analysed their data and initially concluded that the lens was likely lighter, in the range of roughly 1.6 to 4.4 solar masses, with their preferred estimate falling near the lower end of that range. If the true mass was near that low end, the object was more likely a neutron star than a black hole. If it was near the high end, it was almost certainly a black hole. The disagreement, though it looked like a scientific controversy at the time, was actually a healthy demonstration of how astrometric microlensing analysis is done. Both teams were working from essentially the same photometric data from OGLE and MOA, and from largely overlapping sets of Hubble astrometric measurements. But they were making different choices about how to model the Hubble point spread function, how to correct for the crowded stellar field around the lens, how to weight different epochs of data, and how to treat the systematic uncertainties in Hubble's own pointing. Small differences in any of those choices propagated into small differences in the inferred astrometric shift, which propagated into significant differences in the inferred mass. The Sahu team's analysis leaned on the largest baseline of Hubble observations available at the time. The Lamb team's analysis leaned on a more conservative treatment of the point spread function. Neither was wrong. Both were doing careful science under measurement conditions right at the edge of what Hubble was capable of. What eventually resolved the disagreement was the arrival of additional Hubble observations taken during 2021 and 2022, well after the peak of the microlensing event, when the residual astrometric shift from the lensing was still slowly decaying. Those additional data points broke the ambiguity and pushed both analyses toward the same answer. Over the following year, both groups reanalyzed the data, incorporated additional Hubble observations, and refined their models. By late 2022 and into 2023, the analyses converged. The best fit mass settled at roughly 7 solar masses, with an uncertainty of about 1 solar mass. The lens was decisively above the maximum possible mass of any known neutron star, which sits at about 2.3 solar masses. There was no reasonable interpretation left, except that this thing this dark object drifting quietly through the bulge of our own galaxy was a black hole. An isolated stellar mass black hole with no companion, no accretion disk, no radiation of any kind, betrayed only by the fact that a background star had happened to pass almost precisely behind it in the summer of 2011, and by the extraordinary patience of a decade-long campaign to measure the position of that background star to within 1,000th of an arcsecond. That was the first confirmed detection of a free-floating stellar mass black hole in history. It was also, in an important sense, a proof of principle. The technique worked. The predictions of stellar evolution, that the galaxy should be teeming with objects exactly like this one, could finally be tested against real data instead of just theoretical population synthesis. And the detection strategy that had been theorized for decades, long microlensing event, astrometric follow-up, mass measurement, was not just plausible, it had actually delivered. There is a beautiful physical logic to how it all works once you step back. Everything else about a rogue black hole is silent. Its horizon does not emit. Its neighborhood does not glow. Its motion through interstellar space is not accompanied by any signal, but its gravitational field is inescapable, and gravity is exactly the property that gets amplified when it happens to sit between us and a distant source of light. The very feature that makes a black hole in the first place, its enormous mass concentrated in a tiny region, is precisely what makes it lens light so effectively. In a sense, the black hole betrays itself by being what it is. You cannot hide gravity, and gravity is what we hunt with. Since the confirmation of that first event, the pace of the field has quickened considerably. Several other long-duration dark lens events are now being analysed with follow-up astrometric campaigns. Some will turn out to be neutron stars. Some may turn out to be black holes. And in the coming years, the technique will be revolutionized once more by the launch of the Nancy Grace Roman Space Telescope, expected in the late 2020s. Roman will monitor the galactic bulge continuously from space, catching tens of thousands of microlensing events every year, with astrometric precision built into the survey itself, rather than requiring years of separate follow-up. Population studies predict that Roman will detect on the order of a few hundred isolated black holes over the course of its mission. In one instrument, it will do more for the census of rogue black holes than every previous survey combined. The invisible population of the Milky Way is finally about to be counted. In the meantime, several other candidate dark lens events discovered by O, GLE, and MOA in the years before and after 2011 are being reanalyzed with fresh Hubble astrometry campaigns. Some of them appear to be neutron stars, based on masses that fall below the black hole threshold. Some appear to be very faint main sequence stars that were simply too dim to detect against the crowded bulge background. A handful, though, look like promising black hole candidates in their own right. Papers announcing further isolated black hole detections have begun to appear at a rate of 1 or 2 per year, drawn from the accumulated microlensing archive. Each one adds a data point to the mass and velocity distribution. Each one refines the population estimate. None of them individually will be as historic as the 2022 confirmation, because the door has already been kicked open. But collectively, they are the beginning of a real astronomical census of the galaxy's rogue black hole population, built up one careful analysis at a time. By the middle of the 2020s, that census may include 10 or 15 confirmed cases drawn from decades of accumulated survey data. By the end of the decade, Once Roman is operational and delivering its own detections, the number will be in the hundreds. What began as a single event in the summer of 2011 is now a small but growing catalogue of individually identified silent black holes, each one a formerly invisible corpse of a formerly massive star. There is a complementary line of evidence about the population of stellar mass black holes in the galaxy that comes from a completely different direction, and it is worth mentioning because it fits into the same picture. Since 2015, the Laser Interferometer Gravitational Wave Observatory in the United States, joined by Virgo in Italy and later by Kagura in Japan, has been listening for the ripples in space-time produced when two black holes spiral together and merge. The detectors have caught dozens of such events, and the catalogue is growing every year. Each event tells us the masses of the two black holes that merged, and something about the environment in which they formed. Those detections are, in one sense, opposite to the rogues we have been talking about. They are black holes that were bound to each other. They are the ones that did not become rogues, either because they were born as a binary and stayed together, or because they were paired up in a cluster and driven together by dynamics before they could be flung apart. But the same underlying population of massive stars produces both the merging binaries that LIGO sees and the rogues that microlensing catches. The physics of natal kicks, of metallicity, of binary disruption, of cluster dynamics, all of it feeds into both channels. If you have a working model for how massive stars die, that model has to simultaneously predict the LIGO merger rate and the microlensing rogue count. Neither number can be adjusted independently. They are two views of the same underlying population, one seen through the shudder of merging horizons, and the other seen through the bending of background starlight. When astronomers construct population synthesis models today, they are being simultaneously constrained by both. The numbers so far are broadly consistent with each other, which is quietly reassuring. It suggests that the theoretical machinery we have built to model the deaths of massive stars is capturing at least the rough shape of reality, and it suggests something else. It suggests that the enormous invisible population of rogues we have been talking about is real, is out there, and is roughly the size the models predict. Independent evidence from a completely different observational technique. Gravitational waves from a completely different subset of the population points in the same direction as the microlensing hunt. The corpses of massive stars are everywhere. Some collide, some drift, but even a full census tells us only where they are statistically. It does not answer the question that most people, hearing about 100 million invisible things drifting through the galaxy, actually want to ask, which is whether any of them, on any timescale that would matter to us, might be drifting toward home. If the population estimates are anywhere close to right, then somewhere within roughly 20 or 30 light years of the sun, right now, there is very probably at least one isolated stellar mass black hole. That statement is not a hypothesis. It is arithmetic. Take 100 million rogues, spread them across the disk of the Milky Way, do the volume math on the neighborhood around the sun, and the number that falls out is close to 1, maybe 2, almost certainly not 0. There is a black hole in our stellar neighborhood. Nobody has ever seen it. We do not know its name, we do not know its exact distance, we do not know which direction it is drifting. But statistically, it is there. Sit with that for a moment, because it is the kind of statement that sounds terrifying, and then, on inspection, turns out to be almost the opposite. because the Milky Way is enormous, and the neighborhood of the Sun, even when we describe it as a sphere 20 or 30 light years across, is by any human standard unimaginably large. So the fact that a black hole probably shares that sphere with us tells you very little about whether it is anywhere near us in any meaningful sense. Consider what 20 light years actually contains. It contains roughly 130 known stellar systems, most of them dim red dwarfs invisible to the naked eye. Between those systems is a volume of interstellar vacuum so vast that if you shrank the Sun to the size of a beach ball and placed it in New York City, the next nearest star would be represented by another beach ball sitting somewhere in Chicago. That is the density of stars in our neighborhood. That is what close means in the galactic disk. 2 beach balls, hundreds of miles apart, with essentially nothing between them but empty space, now scatter on top of that thin population of stars, a much thinner population of invisible black holes, at some tens of light years typical separation from one another. The nearest rogue to the Sun, wherever it is almost certainly farther from us than the nearest known star. It might be 12 light years away. It might be 25. It might be 40. It might be doing a slow, aimless drift that will keep it at roughly the same distance from us for the next 100,000 years, because its motion happens to be roughly parallel to ours. And it might, in a purely statistical sense, be very slowly closing the gap. But the words closing the gap have to be understood on their proper timescale, which is millions of years, not weeks or centuries. To feel that timescale, you need to understand how stellar close encounters actually work in the disk of a galaxy. The disk is a chaotic but slowly evolving system. Everything in it is orbiting the galactic center in the same general sense, moving in the same broad direction, but each star, each stellar remnant, has its own personal velocity relative to that broad flow. Those personal velocities are called peculiar velocities, and for stars in the Sun's neighborhood, they are typically a few tens of kilometers per second. Some are moving faster, up to a couple hundred kilometers per second, but most are relatively slow. That means that although stars are moving, they are not zooming past each other. From our perspective, the entire sky is nearly frozen. Even the nearest star to the Sun, Proxima Centauri, is closing on us at a modest 22 kilometers per second. Over 1,000 years, it will move by about 700 billion kilometers, which sounds like a lot but is barely a 50th of the distance between us and it. Stars in the disk drift past one another the way icebergs drift past one another, ponderously, on timescales that make human history feel like a snapshot. Rogue black holes drift no faster than that. Their velocity distribution overlaps with that of ordinary stars almost completely, because their extra kick from birth is only a modest boost above what a random star already has. So a rogue black hole in our neighborhood is not screaming toward us or away from us. It is moving at most, 100 or 200 kilometers per second in some direction. It will take that black hole hundreds of thousands of years, and often millions of years, to change its distance from the Sun by any significant fraction of a light year. That already tells you something honest about the risk profile. But the truly disciplined way to think about it is to look at the actual history of what has come close to the Sun in the past. Astronomers have spent the last decade or two doing exactly this work. They have taken the modern star catalogue, run stellar orbits backward and forward in time using the best available data, and identified which stars have made, or will make, unusually close passes through the Sun's neighborhood. The list is short, and it is illuminating. The most famous case is a small binary system known as Schultz's star. catalogued formally as WISE 0720-0846. It is a dim red dwarf paired with an even dimmer brown dwarf companion, sitting today about 22 light years away from us and receding. In 2014, an astronomer named Ralph Dieter Scholz noticed something odd about its motion. Its proper motion, meaning its apparent drift across the sky per year, was surprisingly small for such a nearby star, and its radial velocity, meaning its speed toward or away from us, was surprisingly large. Both of those clues suggested that the star was moving almost directly along our line of sight rather than across it, which is exactly the signature you would expect if you had recently passed near a star and were now watching it recede almost straight away from you. A team led by Eric Mamajek at the University of Rochester followed up, integrated the star's orbit backward, and found that Scholz's star had passed within about 0.25 light years of the Sun approximately 70,000 years ago. 0.25 light years is very close by any galactic standard. It is deep inside the Oort cloud, well inside its outer edge, the vast spherical shell of icy bodies that surrounds the solar system out to distances of about 1 light year or more from the Sun. For a brief moment in the deep human past, when our species had already spread out of Africa and was crossing into Western Asia, another star was ambling through our own comet reservoir, and nothing dramatic happened. There is no signature in the geological record, no wave of impacts, no discernible perturbation, no mass extinction linked to this pass. The Oort cloud is so diffuse that a passing star's gravitational tug barely stirs it. Perhaps a small percentage of long-period comets that we see today were nudged onto their current orbits by that encounter, but even that is speculative. The main lesson is that even a very close stellar pass, well inside the outer solar system as we usually draw it, produced essentially no effect that anyone alive during the encounter could have noticed. The other landmark case is a star called Gliese 710. It is a modest orange dwarf currently sitting about 62 light years from Earth in the constellation of Serpens Cauda, moving slowly in our direction. The orbital calculations, refined most recently with data from the Gaia Space Observatory, suggests that Gliese 710 will make its closest approach to the Sun in approximately 1.3 million years. And at that time, it will pass within roughly 0.17 light years of us. That is about 10,000 astronomical units, well inside the Oort cloud, closer than Scholz's star came. It is one of the closest stellar approaches to the Sun expected in the entire foreseeable future of the solar system. And even for this genuinely close pass, the expected consequences are quite modest. Detailed simulations suggest Gliese 710's flyby will send a modest additional shower of long-period comets toward the inner solar system over a span of perhaps a few million years after the encounter, which may increase the impact rate on Earth by some small factor above the background rate for a while. Nothing that would end life on Earth, nothing that would derail the Earth from its orbit, nothing that any inhabitant of the solar system, if there's anyone here in 1.3 million years to see it, would experience as anything other than a slightly brighter than average star for a very long time, and then a slightly elevated rate of interesting comets in the following geological era. That is what a genuinely close stellar approach looks like. It is exceedingly gentle by any human standard. And when astronomers integrate all the stars whose motions we know well enough to trust the calculation, they find on the order of one such approach every several 100,000 years, on average. Occasionally, on much longer timescales, a star may pass even closer than Gliese 710 will. The very rare events, closer than a few thousand astronomical units, seem to happen a few times per 100 million years. Now, everything we just said applies to visible stars, the kind Gaia can catalogue. Rogue black holes are not in that catalogue. And here is where the epistemically responsible framing starts to matter, because it is very tempting to say, and therefore we do not know whether a black hole is closing on us right now, and let the audience's imagination fill in the rest. But that framing overstates the mystery. Because although we cannot directly track individual rogue black holes, we can and do reason about the population as a whole. Statistical astronomy is a real discipline, and the statistics tell us something clear. The population of rogue black holes in the solar neighborhood is not more numerous than the population of ordinary stars. It is much less numerous. Even the most generous population estimates put isolated stellar mass black holes at roughly 1 for every 1,000 ordinary stars in the disk. So if the rate of close stellar approaches to the Sun is 1 every couple 100,000 years, the rate of close black hole approaches must be very roughly 1 every couple 100 million years, perhaps less often. And the definition of close we are using here is still very generous. It means passing within a light year, well inside the Oort cloud, which, as we already established, is essentially harmless. The rate of a rogue black hole passing close enough to genuinely affect the inner solar system, closer than a few tens of astronomical units, closer than the outer planets, is far smaller still. Order of magnitude estimates put that kind of encounter at roughly 1 per 100 billion years, if not less often. The Milky Way is only about 13 billion years old. The universe as a whole is only about 13.8 billion years old. If the numbers are anywhere near right, no rogue black hole has ever come close enough to seriously disturb the inner solar system in the entire history of our star system, and none is expected to before the Sun itself dies. This is the honest picture. The galaxy is full of these things, and yet none of them, in all likelihood, has ever come close enough to matter, and none of them is likely to before the Sun runs out of hydrogen. But saying no rogue black hole is heading for us would still be too strong a claim, because we do not have a catalogue of them, and we cannot rule out individual cases. So the correct phrasing is more careful. The population statistics make a genuinely threatening close pass so improbable on any timescale that has ever mattered to life on Earth or ever will, that no serious astronomer treats it as a scenario worth planning for. The public conversation about killer black holes tends to strip away that qualifier and turn improbable on a timescale of hundreds of billions of years into could happen at any moment. Those are not the same statement, not even close, which brings us to the tools we use to keep tabs on what actually is out there and how the situation may improve. The most important instrument in that story is the Gaia Space Observatory, launched by the European Space Agency in 2013 and still operating today. Gaia sits at the second Lagrange point of the Earth-Sun system, about 1.5 million kilometers from Earth on the anti-solar side. From that vantage point, unbothered by the atmosphere or the Earth's day-night cycle, it steadily scans the entire sky, over and over, measuring the positions of stars with a precision that would have seemed like science fiction only a generation ago. Its current data release, the third one, catalogues the positions, distances, and motions of nearly 2 billion stars across the Milky Way. For the stars closest to the Sun, its precision is such that it can measure their proper motions to a few micro-arcseconds per year, which means it can predict where each star will be, relative to us, 1,000,000 years into the future, with real accuracy. It is Gaia's data that pinned down the orbital predictions for Gliese 710 and for dozens of other close approach candidates. Without Gaia, our knowledge of the immediate stellar future would be a shadow of what it is today. But Gaia has a fundamental limit. It sees stars, it sees light, and a rogue black hole, as we established at length, emits no light. So Gaia cannot see rogue black holes, it cannot catalogue them, it cannot predict their orbits, it cannot warn us if one is approaching. In this specific respect, our all-sky map has a systematic gap. An entire population of massive objects that our best census instrument is blind to. This is not a flaw in Gaia. It is a fundamental limitation of any survey that depends on collecting photons. Photons are what rogue black holes do not emit. There is, however, one indirect way Gaia can contribute to hunting rogues, and it is quietly building. If a rogue black hole passes close enough to a visible star, its gravity will slightly perturb the star's motion. In principle, if the encounter is close enough and long enough, Gaia's exquisite astrometric measurements might detect that perturbation as a subtle wobble in the star's trajectory. In practice, the geometry required is rare and the signals are small, but there is also a second astrometric application, closer to the microlensing story we already told, when a rogue black hole passes almost directly in front of a background star. Gaia's astrometric time series can potentially detect the tiny position shift of the background star during the event, complementing the brightness data from ground-based surveys. Several tentative candidates for rogue black holes have been proposed on this basis, and the analysis of Gaia's later data releases will likely turn up more. None of these techniques will tell us where any specific rogue is right now, and none will detect a rogue that happens to be drifting through the deep vacuum without passing near any convenient background star. But the population will slowly, gradually come into view. Roman, when it comes online, will not tell us about any specific rogue drifting through the Sun's neighborhood, because its field is aimed at the crowded bulge on the far side of the galaxy where the microlensing statistics are richest. But what it will do is characterize the population as a class. It will measure the mass distribution and the velocity distribution of rogue black holes for the first time. It will let astronomers ask, with real data instead of pure inference, how many rogues there really are, how heavy they run, how fast they move, and how their velocities are distributed relative to the disk. And once we know those numbers with confidence, we can back out far more accurate statistics on how often, on average, one of them wanders anywhere near the solar neighborhood we live in. The theoretical population estimate of 100 million becomes a measured number. The inferred crowd of ghosts becomes a counted census. There is a related question worth confronting, which sometimes comes up in casual discussion of this topic. If a rogue black hole were on a genuine collision course with the solar system, when would we know? The answer depends heavily on what on a collision course means, and on how close the black hole was when it first entered a range where any instrument could plausibly detect it. Consider the specific scenario of a rogue black hole approaching the Sun from, say, 1 light year away, moving at 70 kilometers per second on a trajectory aimed directly at the inner solar system. At that distance and speed, it would take the black hole approximately 4,000 years to arrive. Would we spot it during those 4,000 years? Very possibly, yes, but only if we were extremely lucky with the timing of a background alignment. As the rogue approached, its gravitational field would bend the light of any star that happened to pass behind it from our perspective, producing a slow, drawn-out microlensing event. If astronomers happened to be watching that patch of sky at the right moment, they would see a foreground shift and a brightness change consistent with a stellar mass dark lens at a relatively close distance. That would tell us something is there. In the years and decades that followed, refined astrometric follow-up would pin down its mass, its distance, and its trajectory. If the object was on an ordinary passing course, the announcement would be interesting but not alarming. If, hypothetically, the trajectory pointed directly at the sun, the announcement would be historic. That said, the probability of that being the outcome, given everything we know about how the galaxy actually works, remains stupendously small. There is also the question of what we would do about it, and the answer here is easy. We would do essentially nothing, because there is essentially nothing that could be done. Even the most ambitious space engineering imaginable would offer no meaningful defense against a stellar mass black hole passing through the inner solar system. But this is very much a hypothetical concern. It is worth understanding purely as a way to internalize the scale of what we're talking about. It is not, in any responsible framing, something for anyone to lose sleep over. The deeper reason for calm is not simply that the odds are small. It is that the odds are small on a specifically physical basis. Rogue black holes are drawn from a population of 100 million objects spread through a galactic disk that is enormously larger in volume than the region within which their effects on the sun would even be noticeable. The ratio of dangerous volume to total volume is comically tiny. Multiply that by the time available across the entire remaining lifespan of a habitable Earth, roughly 1 billion years before the sun becomes too luminous for surface water. And the expected number of dangerous encounters is a fraction so small that treating it as zero is a perfectly reasonable simplification of reality. But rogues are still worth caring about. Not because any specific one threatens us, but because their existence, and our ability to detect them, tell us something fundamental about the galaxy. They are the corpses of every massive star that has ever died. They are the invisible tail of every stellar cluster that has ever dissolved. They carry, in their masses and their velocities, the accumulated record of billions of years of stellar death and dynamical chaos in the Milky Way. Learning to see them, even indirectly, is learning to read a chapter of galactic history that no other technique can access. And the question people always want to ask, even after all the honest caveats, is still worth asking cleanly and directly. What would happen, actually, if a rogue black hole did come close? Not passing at 1 light year, where the effect is negligible. Not passing through the outer Oort cloud, where the effect is a slow rain of extra comets over the next few million years. But genuinely close. Passing through the outer solar system where the planets orbit, or, more extraordinarily still, through the inner solar system itself. What does that do? Let us try to answer that cleanly, in stages, because the honest picture depends entirely on how close is close. A rogue black hole does not have a single fixed effect on the solar system. It has a graded effect that scales dramatically with the distance of closest approach. So let us walk through the scenarios in order, from the ones that produce almost no consequence to the ones that end the solar system as a stable planetary system. That way, by the end, the shape of the risk is fully visible. Start with the least dramatic scenario. A rogue black hole passes through the sun's larger neighborhood, closest approach 1 light year. That is about the outer boundary of the Oort cloud, and it is roughly 4 times farther out than the closest passage that Schultz's star made in the deep human past. The effect on the solar system is, in almost every measurable sense, nothing. The inner planets do not notice. The outer planets do not notice. The sun is not perturbed. The event happens quietly over a span of perhaps 10,000 years, as the black hole crosses through the outer solar neighborhood, and the only thing that changes is a small statistical perturbation to the orbits of Oort cloud comets. Some of those comets will be nudged onto trajectories that eventually carry them into the inner solar system, becoming spectacular long-period visitors thousands or millions of years later. But even that effect is tiny compared to the ordinary background rate of comets. If human civilization survived to witness such a pass, it would be an extraordinary astrophysical event, worthy of enormous scientific attention, and it would have no impact whatsoever on daily life. The night sky would look unchanged. The sun would rise and set on schedule. The Earth would remain exactly where it is, doing exactly what it has always done. That is what a close pass at a light year actually means, physically. Almost nothing. Now tighten the geometry. Bring the black hole in closer, to a closest approach of, say, 1,000 astronomical units. That is about 25 times the distance from the Sun to Neptune. It is well inside the Oort cloud proper, but still far outside the region where the planets live. The gravitational tug of a 10 solar mass black hole passing at that distance is significant enough that the effect on Oort cloud comets is no longer subtle. Detailed simulations of such passes suggest that a substantial fraction of the Oort cloud, perhaps 10 or 20%, is either stripped away entirely, torn loose from the sun's grip and carried off with the black hole, or scattered onto new inward orbits that will slowly rain comets into the inner solar system for tens of millions of years afterward. The impact rate on Earth during that era of extended cometary rain would climb by perhaps a factor of 10 above background. That is not a mass extinction rate. It is not even necessarily a rate that a well-established civilization could not endure. But it is a genuinely elevated impact rate that would leave a signature in the geological record of any world in the solar system, including ours. Meanwhile, the inner planets themselves feel almost nothing directly. The gravitational perturbation of a distant point mass 1,000 astronomical units away on Earth's orbit is far too small to measure, let alone to be dangerous. Earth's orbit is essentially untouched. Life on Earth proceeds normally, occasionally interrupted by a somewhat elevated rate of comet arrivals in the deep future. Bring the black hole in closer still, to a closest approach of 100 astronomical units. Now we are on the order of the outer edge of the classical Kuiper belt, past the orbit of Pluto, but still well outside the giant planets. This is where things begin to get genuinely interesting from the solar system's point of view. A 10 solar mass object passing at 100 astronomical units delivers a gravitational impulse large enough to seriously disturb the outer solar system. The Kuiper belt is scattered violently. A substantial fraction of the trans-Neptunian population is either ejected from the solar system or thrown into wildly eccentric orbits that will bring them into the inner system over the following few million years. Neptune, Uranus, and possibly Saturn feel meaningful perturbations to their orbits. Their eccentricities may be pumped up, their inclinations tilted, their orbits made less stable on the long time scale. Whether the outer planets remain in stable, planet-friendly orbits after such an encounter depends sensitively on the exact geometry of the pass. In many simulated cases, the outer planets survive but with somewhat altered orbits, and the solar system settles down into a new but recognizable configuration after a few tens of millions of years of dynamical readjustment. The inner planets, protected by their smaller orbital radii and by the sun's dominant gravitational grip on them, mostly ride it out. Earth is still in the habitable zone. The sun still shines on it. But the outer solar system is a mess for a long time, and the elevated impact rate on Earth from all those newly scattered outer bodies is severe. This kind of pass would produce a very distinct geological signature on any planet in the inner solar system. Now tighten further to a closest approach of 10 astronomical units. That is roughly the orbital distance of Saturn. Now the black hole is passing through the giant planet region. This is where the assumption that Earth is safely tucked inside starts to break down. The perturbation on Saturn's orbit, if Saturn happens to be nearby during the pass, could be enormous. The giant planets are heavy enough that the black hole cannot casually strip them off individually, since gravitational binding to the sun at that distance is still very strong. But the geometry of a pass can send one or more of them into wildly different orbits, and the aftermath of that can propagate inward. Numerical simulations of close stellar or black hole encounters at this range often show one or more of the giant planets being ejected from the solar system entirely, hurled onto trajectories that carry them into interstellar space, where they become rogue planets themselves. Others are captured by the intruder as it departs, leaving the solar system carrying newly stolen worlds with it. The remaining planets settle into a rearranged and often unstable configuration. The inner solar system is now in trouble. The removal or rearrangement of Jupiter and Saturn, in particular, would have profound consequences for the long-term stability of Earth's orbit. Because Jupiter's gravitational shepherding of the inner solar system is not a small effect. Without Jupiter, or with Jupiter on a very different orbit, the terrestrial planets are far more vulnerable to mutual gravitational chaos over millions of years. Tighter still, to a closest approach of 1 astronomical unit. That is Earth's orbital distance. That is the black hole passing through the inner solar system. At this range, the direct gravitational perturbation on Earth's orbit is severe. Whether Earth remains bound to the sun at all after such an encounter depends on the exact timing, on where Earth happens to be in its orbit when the black hole passes, and on the geometry of the trajectory. In many simulated cases at this range, Earth is either ejected from the solar system entirely, becoming a rogue planet itself, freezing solid over the following 1,000 years as it drifts into interstellar darkness, or captured by the passing black hole, thrown into a wildly eccentric orbit around the intruder as it leaves, or dropped into the sun by the disruption of its orbit. All three outcomes are lethal for anything living on Earth's surface. The end of life on Earth in this scenario is not caused by the black hole absorbing anything or destroying anything through its horizon. It is caused entirely by the removal of the delicate orbital conditions that make Earth habitable. Earth does not need to be swallowed to die. It only needs to be moved. And even in the extreme scenario of a black hole passing directly through the inner solar system, actual physical collision between the black hole and Earth, or between the black hole and any planet, remains vanishingly unlikely. This is a point that is worth internalizing carefully because it is genuinely counterintuitive. A 10 solar mass black hole has an event horizon roughly 60 kilometers across. Earth is a target 12,700 kilometers across. And the inner solar system is a region roughly 300 million kilometers across. The odds of a randomly directed trajectory through the inner solar system actually intersecting Earth's disk are astronomically small. The overwhelmingly likely outcome, even in a very close pass, is that the black hole moves through the solar system without touching anything, gravitationally rearranges the planetary orbits along the way, and departs into the interstellar dark, carrying no material with it. The catastrophe is in the gravitational disturbance, not in the direct impact. Impact is essentially impossible on any reasonable geometry. Rearrangement of orbits is the real hazard. There is one more scenario that is worth walking through, mostly because it is the one that pops into people's imagination first, even though it is the least likely of all. What if the black hole did strike Earth? What if the trajectory happened to be threaded through the eye of a needle so narrowly that the 60-kilometer horizon actually swept across the Earth's diameter? The answer is that it would be over very quickly. A 10 solar mass black hole moving through Earth at, say, 200 kilometers per second would pass through the entire planet in about 1 minute. Along its path, it would consume everything within a few hundred kilometers, drawing rock and iron directly into its horizon. The tidal forces on the rest of the planet during that minute would tear the outer crust into fragments, ignite the interior through violent compression, and leave behind, once the intruder emerged from the far side, a shattered remnant that would not resemble a planet in any meaningful sense. The remaining fragments would be gravitationally recollected by the sun and would eventually form a new asteroid belt, or a very thin ring, plus some fraction that was ejected. Earth would be gone. Nothing that had lived on it would survive. There was no world in which any life form could ride out that scenario. But again, and this is the essential point, this outcome requires an alignment so ridiculously precise that even in a very close pass through the inner solar system, it essentially never happens. The gravitational catastrophes are the real risk. The direct swallowing is a curiosity. Step back from all of that and remember the framing we have carefully built. The population of rogue black holes drifting through the Milky Way is enormous. Their velocities are not extreme. Their motions are essentially random with respect to the sun, which means that on any given epoch, the fraction that happens to be pointed anywhere near us is minuscule. The rate at which one is expected to make a genuine close pass closer than a light year is on the order of once every 100 million years or so. The rate for a truly threatening pass, one that would actually disturb the inner solar system, is far smaller than that, on the order of once every 100 billion years or more, which is longer than the current age of the universe. No such event has occurred in the entire history of our solar system. The Earth is 4.5 billion years old, and by every geological, geochemical, and orbital indicator we can measure, no rogue black hole has ever come close enough to us to leave a trace. The rogues have been out there the entire time. They just have not been anywhere near us. And in all likelihood, they will not be anywhere near us for the remaining habitable lifetime of our world. So why do we care? Why do astronomers hunt for these things at all? And why have we spent an entire evening talking about them? If the answer is that they are almost certainly harmless, the answer is that a rogue black hole is one of the purest examples of something that science does exceptionally well, which is to reason about invisible things through their unavoidable effects. A rogue does not shine. It has no companion. It moves too slowly to be caught by any change we could notice on a human timescale. It has no accretion disk, no jet, no signature in any part of the electromagnetic spectrum. It hides in a way that almost nothing else in the galaxy hides. And yet, through the single loophole of gravitational light bending, we have caught one. We have measured its mass, we have located it in space, we have watched it move. The fact that this is possible at all is a remarkable statement about what the human enterprise of astronomy has become. We have built the tools and worked out the mathematics and organized the international collaborations needed to find a black hole that emits no light. That is not a small thing. There is also a deeper physical reason that rogue black holes are worth caring about, quite apart from their inability to threaten us. Every rogue black hole in the Milky Way is a piece of stellar history preserved in dark form. Each one is the ghost of a massive star that lived briefly and died violently. Either in a supernova whose kick propelled the remnant into interstellar space, or in a failed supernova that dropped the remnant quietly into the void, or in a stellar cluster whose dynamics eventually flung the remnant free. When we count rogues, we are counting the deaths of massive stars across the entire history of the Milky Way, all the way back to the earliest generations of stars that formed shortly after the birth of the galaxy. The population of rogues is a fossil record. It records the initial mass function, the shape of star formation, the rate at which stars have been dying, the frequency of failed supernovae versus successful ones, and the strength of the natal kicks. Every one of those quantities is deeply informative about the physics of stellar evolution, and every one of them is difficult or impossible to measure directly from any other technique. The rogues are, in effect, a hidden census of the Milky Way's most spectacular stellar deaths. Learning to count them is learning to read a chapter of the galaxy's biography that no other method can access. There is a third reason, which is even more general. Everything we have talked about in this discussion has been about stellar mass black holes, weighing a few solar masses, drifting through interstellar space. But the general problem of finding dark, massive objects through their gravitational effects on background light is central to a great deal of modern astronomy. The same technique that caught the first rogue black hole, gravitational microlensing combined with astrometric follow-up, is being used to search for dark matter, to constrain the population of primordial black holes that may or may not have formed in the earliest moments after the Big Bang, to probe the mass function of low-mass stars and brown dwarfs, and to measure the masses of individual stars in ways that no other technique can achieve. Every improvement in our ability to find rogue black holes is also an improvement in our ability to answer these other, still open questions. The Nancy Grace Roman Space Telescope, when it launches, will not only revolutionize the census of rogues, it will simultaneously deliver a step change in our understanding of many other populations of dark or dim objects in the galaxy. The rogues are the leading edge, but they are not the whole story. And there is, finally, a genuinely humbling thought that emerges from all of this. We tend to think of our galaxy as being made of stars, because stars are what we see. When we look up at the night sky, the stars are the entire population of the Milky Way as we experience it. We know intellectually that there is a great deal of gas and dust between the stars, and we know that there is a great deal of dark matter surrounding the visible galaxy. But there is a third population that we have only recently begun to appreciate in earnest, and that is the population of stellar corpses. The Milky Way contains, in addition to its roughly 200 billion visible stars, an estimated 1 billion neutron stars, and something like 100 million or more stellar mass black holes. Almost all of those neutron stars and almost all of those black holes are dark, cold, or otherwise invisible. When you add them up, the total mass locked in stellar remnants that we cannot easily see is a significant fraction of the mass of the visible stellar population itself. Our galaxy is not just made of stars, it is also made of the dead husks of stars, of the corpses of the most massive members of every generation of stars that has ever formed. Those corpses drift among the living stars, unseen, in enormous numbers. The Milky Way is, in a very real sense, more of a graveyard than we usually recognize, and the shining stars we see are just the currently living portion of a much larger and much older population. That is what a rogue black hole really is. When you strip away the science fiction associations that the words black hole carry, it is the quiet, invisible remnant of a star that died a very long time ago, drifting through a galaxy that has forgotten it. It is not hunting us. It is not aimed at us. It is not accelerating toward the solar system. It is simply moving in whatever direction the events of its distant past sent it, at whatever modest velocity the physics of its birth or ejection gave it, through a galactic disk so vast and so empty that the odds of it coming anywhere near us on any timescale that matters are almost unimaginably small. And yet it exists. It is out there. There are 100 million or so of them doing exactly this right now, and one of them is very probably closer to the sun than the nearest visible star. And none of them are dangerous, and the human beings who figured all of that out are the same species that a couple of centuries ago did not know that our galaxy was one galaxy among many, and were not entirely certain that atoms existed, and could not see anything in the sky that was not lit up by ordinary photons. The story of the rogue black hole is, in that sense, one of the quiet triumphs of modern astronomy. It is a story about learning to see the invisible. It is a story about extracting a measurable signal from an object that has essentially no direct signal to give. It is a story about patience across decades, about international collaborations across continents, about combining a ground-based survey in Chile with another ground-based survey in New Zealand, with a space telescope in low Earth orbit, and analyzing the combined data with statistical machinery of astonishing sophistication, all to catch one bending of the light of one star behind one drifting corpse of a star that died in a supernova millions or perhaps billions of years ago, somewhere else in the galaxy. And by doing that, one time in 2022, humanity confirmed the existence of a category of object that had been predicted for decades but never seen. And in doing so, we opened the door to seeing hundreds more in the years to come. The next time you look up at the night sky and pick out a bright star and ask yourself, what is really out there in the darkness between the stars? Remember this. Some of what is out there does not shine. Some of it is heavy and old and moving and completely silent. Some of it will be found in the coming years, one careful microlensing event at a time, by patient astronomers watching for the moment a distant star flickers because something dark and heavy slid in front of it. Some of it may already be closer to us than the nearest star we can see. And none of it, in any way that will ever affect anyone alive today, or for anyone alive tomorrow, or anyone alive for a very long time to come, is heading anywhere near us. The rogues are the galaxy's ghosts. They are drifting in their own quiet paths, and now, for the first time in the entire history of our species, we are starting to see them